Good afternoon, good evening, good morning, everyone. My name is Jakub Dakowski. I'm from the Adam Mickiewicz University in Poznań. And this will be a talk on the isomorphism between Sudoku and proof systems and the application of this isomorphism in solving Sudokus. So in a way, it will be slightly a different presentation from the last two we saw here. However, I still think that there is multiple things in this, especially in the discussion, that are worth mentioning or discussing. So to start us off, let's ask ourselves what is a Sudoku. It's a 9x9 matrix filled partially with numbers or digits from 9 to 1 or from 1 to 9. And it has rows and columns, as you might imagine. And it also has these 3x3 subgrids, which usually or sometimes are, and also here are marked with this bolder line that you can see here. And also, well, how do you solve a Sudoku? Basically, we need to fill the Sudoku in such a way that no digits reappear in a given row, column, or subgrid. And an important distinction is that multiple papers actually consider Sudokus, only Sudokus that have one solution, a Sudoku. I am not using that limitation here. Every Sudoku that has at least one solution is considered. So now, how do we solve Sudokus? We have, well, basically, we have this set of strategies, which are these methods of transforming Sudokus into different solvable Sudokus. Two of the most trivial ones are naked single. This basically says that if in a given field only one digit can be placed into this field will have this digit in this field. That's kind of self-explanatory. Basically, as you can see here, if we do not have a 5 in a field that only can host a 5, this will be there will be a 5 in this situation. Another strategy is hidden single. This is, in my opinion, quite the reverse, because in this situation, we actually ask ourselves if there is a digit that, if there is only one field into which a given digit can be placed in. So here we were discussing whether there is only one digit possible in the field, and that here only one field is possible for the digit in a given column, row, or a subgrid. As you can see here, 3 kind of blocks the rest of the fields for us, so we can place the 3 in this red field. And now let's jump into a different region of human knowledge. So proof systems or proof methods. First of all, the first example is the Hilbert systems, also called axiomatic systems or Frege systems. These work by summoning some axioms. So we start with a set of axioms. Here there are 3 axioms that we use in propositional logic. And then we modify those axioms, we transform them to reach a certain statement that we want to prove. And in natural deduction, this is another system. It works in another way, because we start with an assumption, and this assumption actually starts a subproof. And in this subproof, we can decompose the assumption. Here is the assumption, if you can see my cursor. And here we have the process of the decomposition and composition of what came out of this assumption. And then when we reach what we want, we can just dissolve the assumption, and here we dissolve it by introduction of an implication, and we basically get a sentence that says, if the assumption is true, then something is also true. And well, one can see that there is a certain similarity between the Sudoku strategies and the inference rules used in both the Hilbert systems and natural deduction. And this similarity is really interesting because it's deep. we have these fundamental objects, a formula in the case of in case of logic, and a Sudoku matrix in case of Sudoku, which we transform using some reasoning schemas, proof rules, or Sudoku strategies to create some kind of a desired form. So something that's true, or some proof or some statement, or a Sudoku that's solved. So we try to preserve this truth or solvability. And there is also this, like the other side of the coin, so the negation of truth and the negation of solvability, contradiction and unsolvability. These are really interesting because as we will see later, these can still be used in the process of both proving and Sudoku solving. So we can use this isomorphism. We can take what we know from logic, a concept of consequence operation. It's used to define. It's used to create a set of every derivable statement from a given set of statements. Here, I modified this operation to basically encompass Sudokus. So we have a consequence operation that calculates every Sudoku that's derivable from a given Sudoku with using these two strategies that I've already showed you. And what is important is that in the rest of this talk, I will focus on the Sudoku that has the most filled fields from this set that we achieve from this operation. And another assumption that's important is that I assume that both of these rules actually commute with each other. I use this, I implement this operation using Herbrand models, but that's not really important right now. I can tell you later.
Sorry, maybe a question. You said that the rules commute with each other. I don't understand.
Oh, okay. So
you want to say in Polish, I can translate or something.
Well, I actually think that this is the right translation.
Okay. Please explain then.
In Polish, it's, I think, naprzemienność. What I mean is that no matter in which order we perform these rules, the results will be the same, basically. And so, yeah, thank you very much for the question. And when it comes to the implementation, I can go back to it if you want to. And now, as you can probably see, using this consequence operation, we can already imagine a system that is able to solve some Sudokus. And it's true, the system is able to solve Sudokus, but unfortunately not all of them. There is a problem with incompleteness of this algorithm. And it is possible to create a complete version of this algorithm. I actually have a proof sketch in my mind. You can basically create a rule for every Sudoku solution and just match them. And this will be a complete set of these rules, but this is tremendously inefficient. And also searching for smaller sets of proofs is tremendously inefficient because it would still need a lot of resources and computing power. So I've taken another tool from the proof theoretic toolbox called proof by contradiction from natural deduction. As you can see here, this is basically creating an assumption that P and not P. And then we decompose this assumption into a contradiction. Here is our falsum. And then we can dissolve this assumption using a negation rule, which basically tells us that if something leads to a contradiction, we can assume the negation of it. So this is what we do here. And we can create the same rule for the Sudokus. So on the left, you have the negation rule of natural deduction. On the right, you have a negation rule for the Sudoku calculus, let's call it that way. And this resembles how actually tree search works. So we start from a given point, we create all of the possible consequences in this point. And then if the Sudoku is not filled, we can create an assumption. We again create consequences. If no contradiction is found, we create another assumption. And now let's imagine that a contradiction was actually found. So we can backtrack to the A point from the B point. And now we know that the assumption that we created in B is false. So we already know something, even though we didn't really reach a solution. And again, we can create another assumption. We can go to C. And this assumption can be also incorrect. So we will backtrack to A. And because we have searched through all of the assumptions, there is still a contradiction. There still exists a field that doesn't have any possible value. So we can backtrack to 0. There is a unsolvable Sudoku in the A point. So we can backtrack to the 0 and create another assumption. And hopefully we will find a solution there. And now this actually works. I have tested this algorithm on 96 example Sudokus. 50 of them were easier ones, and the average solving time was 43 milliseconds. And for the second set of harder Sudokus, the solving time was 64 milliseconds. There is also, when it comes to the standard deviation, you can see how big was it. It is understandable that for the second set, the solving time was quite bigger because, as I've already mentioned, this set was harder than the first one. However, basically the same algorithms were already proposed by Peter Norwood in 2006. He used constraint programming to arrive at this algorithm, and Santo, Garcia, and Palomino in 2007, and they also proposed this algorithm from the perspective of a concept called rewriting logic. However, in my opinion, this work is still valuable because, first of all, my goal was not to create the most useful Sudoku solver. It was to propose a concept of using proof theoretic tools to create a Sudoku solving mechanism, and to show that these two processes actually are analogous to each other. And in my opinion, this was successful. Not only that, but the fact that another authors are claiming that this algorithm is complete, so it solves all Sudokus, supports my thesis that it is actually possible to use proof theory to arrive at such concepts. And it is also interesting that Peter Norwood came from the background of constraint programming, because as with generative grammars, there is this concept that we can use generative grammars both to match certain formulas and to generate certain formulas. We can also see this mechanism here in work. So from my perspective, I was generating new solutions and I have arrived at a certain algorithm, and Peter Norwood was actually trying to reduce the amount of possible solutions. He was narrowing down the possible solutions, and he also arrived at this algorithm. So there is this concept of generating and matching via some formal mechanisms. And when it comes to the future work that can be also done, it would be great to actually create a proof of the commutative property assumption. It would be also useful to finish the Hilbert-inspired system I've proposed first, because as I've already said, this is resource consuming, but it can be, in my opinion, it can be done. An actual Hilbert system that starts with all of the solutions, so something that's solvable by definition and allows us to create new Sudokus, would be an interesting concept, especially if we tried doing it for the Sudokus that should have only one solution. We can also use some concepts from logic. So for example, axiom schemas proposed by Fitting, and we actually can use the equivalence classes proposed by Felgenhauer and Jarvis to incorporate these axiom schemas into Sudoku. It is possible, in my opinion, to create tautology puzzles which actually can be solved using any possible digit substitution that is, let's call it, legal in a certain situation. And I see that I've made a mistake here. Unfortunately, more work regarding the relation of proof theory and puzzle solving would be also beneficial, especially as Mary Poppins says, just a spoonful of sugar makes the medicine go down. Work in this field could really improve how we teach logic, how we teach formal sciences, because an example I show in the third point, I think, yeah. So, for example, a solved Sudoku from a modern theoretical perspective can be thought of as a theory. So it consists of all of its consequences. And this is, for example, really interesting because the concept of theory is really hard to grasp when you're starting from logic, where basically there is this infinity explosion right at the beginning. Other similar discussion points is, for example, using this fact to research human deductive skills, and also something which would be also interesting is that maybe we can use similar methods to create more intuitive explanations of both how AI and how formal methods work, not using something that's rooted in math and logic, but something that's actually rooted in things that are intuitive to most of the people. And thank you very much. These are my references. And I think that now is the time for questions.
Any questions to Jakub? Yes, Martin, please.
Okay, sure. So thanks a lot for the presentation. Actually, I do not know anything about Sudoku, but I wanted to ask about if you were thinking of if you try to achieve the same results with, for example, sequent calculus as an alternative for natural deduction. This is the question number one. And the second question is, as you are from Poznań, Adam Mickiewicz University, do you work with Dr. Leszczyńska-Jasion or Dr. Chlebowski?
So maybe I'll start by answering the second question. I actually worked with them. But not on this really. This is actually my mainly my work, because it's not really a graduate paper. It's complicated, but I am really at the graduate level. So I am actually doing my graduate with Professor Leszczyńska-Jasion right now. And
let's get to the topic, okay?
Yes, and as of the
6 minutes for 5
yes. And as of the first question, I haven't tried it, but I think we can achieve sequent calculus for Sudoku. There is this concept of dual tableau, and Sudoku would work really great in dual tableau systems. It's not really related to sequent calculus, but when we are talking about other similar results regarding formalizing these things, dual tableau is, in my opinion, an option that is a great perspective.
Thank you. Any more questions?
Just I have a question.
Yes, please.
How your technique is related to generative grammars?
So, in my opinion, mostly the relation or the analogy of generative grammars is to show this. Well, first of all, both logic and constraint programming are really close to generative grammars, because both logic and constraint programming can be, well, described using generative grammars, if I remember correctly. And it also is interesting because we can think of, it is interesting because there is this analogy, and even when we don't want to think of logic and constraint programming using generative grammars, we can think of them as of, well, a similar analogy. So in generative grammars, we have this analogy of generating and matching solutions. And here we also have this analogy of generating and matching solutions. And in my opinion, it's quite interesting that this is a pattern that arises in different areas.
Thank you for your answer. And I think that it might be useful to you and to your research to learn about grammars with prohibition that are further development of the generative grammars. And you can find these materials on the web, on grammars with prohibition, but also it will be a talk on Friday in the workshop of natural computing. And in this talk, automata, selective machines are introduced. And the main idea is that usually automata or grammars, they generate a language. And the new approach tells that it's necessary to have at least two grammars or two automata, one of which generates a possible language, but the other takes away what's wrong from those language that is generated. And I think the same actually exists in different high-level games like Sudoku or chess, when it's necessary not only to know what's possible to do and what we want to do, but also to know what we cannot do, what are wrong strategies. And so that's why I think that you can gain some new insights in your research from these grammars. And the abstract is also published on the website of Natural Computing in this conference.
Thank you very much, Professor Bergin. We want to rush a little bit because we don't want to be late for your lecture, because many people might come particularly for your lecture. Before I move to Jakub for the last comment, just like I welcomed Professor Bergin, I want also to welcome Brett Martensen, who appeared and who is an expert on pattern classification. So I don't know that you want to have any questions, but it's very good. Thank you very much. Who wants to go next? Maybe some questions. I understand you came a little bit late, but if you have any questions to Jakub, this would be important. And Jakub, what do you want to answer? Jakub, any last words?
Okay, any last words?
Yes.
Okay, so actually, thank you for the recommendation of the grammars with prohibition. I think I will look into that, because that was actually something I was wondering about, like this sort of mechanism. So thank you very much. I will look into it.
And thank you very much. Jakub won the cognitive science competition, where the biggest prize was presentation at our conference, and I'm very happy I organized that.